This is applied physics course for the undergraduate students, and we will study the chapter 7 uh, of Halliday Resnick's book. This chapter is about the systems of particles. I am Dr. Nasir Mirza, and I will be discussing the systems of particles in coming two lectures. For systems of particles, the concept of center of mass is very important. We always say that there is a special point in the system or object, which is termed as center of mass. It moves as if all the mass of the system is concentrated at that point, and the system will move if there is external force applied to the single particle of mass m located at the center of the mass, where m is the total mass of the system. This behavior is independent of the other motion, such as a rotation or a vibration or a deformation of the system. The particle model is valid for such a system, and we convert many particle system into a single particle, employing the center of mass concept. If we have two masses m1 and m2, and they are forming a rigid body, then the center of mass for such system can be defined. This center of mass is located at RCM, the center of mass, and it is given by M1 R1 plus M2 R2 divided by M1 plus M2, where R1 is the uh, position of M1 and R2 is the position of M2, and it is a vector position. And so R is the center of mass is also a vector. Here the coordinate system is shown, and on x-axis these two particles are pointed, and we can see x1 is the distance of m1 from the center, and x2 is the distance of m2, and the center of mass distance is at xcm, and it is near the m2 mass because of the weightage. The m2 is heavy as compared to the m1. If we convert this into the x and y components, the center of mass location can be further elaborated as x center of mass equal to m1 x1 plus m2 x2 divided by m1 plus m2. And the y center of mass is given by m1 y1 plus m2 y2 divided by m1 plus m2. Here you can see that x is weighted with respect to the mass. X1 has a weighting of m1 and x2 has a weighting of m2 as compared to the total mass. So the fraction m2 divided by m1 is a weighting factor which is used for the center of mass. So each position coordinate is weighted according to the mass ratio, the mass of that particle with respect to the total mass. So total mass is m1 plus m2, which is capital M, and we use this to observe that the different masses and different positions can be used to talk about the coordinate of a center of mass. Let us look at the system of particles, and here we have a motion of baton which has a heavy object and a lighter object. You can see a lighter object here and a heavy object, and this is thrown into the air and it is going like this. Now this kind of system, which is roughly two particle system, has a rotation which is overlapping the linear motion. So this motion of the baton is a combination of a parabolic trajectory of that point. That point is the center of mass, as if there was no rotation motion, plus this rotation about that point as if there was no translational motion. And you can see the rotation also, and you can see the linear motion also. Now, if we have the time exposure photograph of this tossed baton with the motion of 3 points, A and B and C, that are indicated by the lights. Uh, then the point A and B show a complex motion. This is the point A and this is the point B, and the C is the center of mass. So you can see the C center of mass is following a simple parabolic path, which is indicating that the center of mass is behaving as if the whole mass is concentrated at that point, and this is the sole representative of the system. So experimentally, we see that the thought about the center of mass is true. We can assume that the center of mass is the uh, point where the mass of the total system is concentrated, and it is moving as if the whole system is concentrated at that point, and the forces are balanced at that point. Let's talk about the motion of a complex object. Our formulation of Newton's laws is based on particle behavior. And sometimes we are able to treat complex objects like particles as if all particles are uh, moving in the same way. But this is not true in general. The rotation about the center of mass and the translational motion of the center of mass makes the motion much more complicated, and we have to have filters. If we fix our attention to special point associated with the object, then the analysis is simplified. So what we do is uh, we say that the center of mass of the object is simply following the Newton's laws. The rotation about the center of mass can be analyzed independently as compared to the translational motion. So the complex motion can be uh, divided or simplified into two or more parts. Let us consider two-particle system. If there are two masses, A and B, connected at the end of a thin rigid rod of a fixed length, and a negligible mass is associated with that rod, then gravity and the normal reactions are classified as external forces. However, tension force exerted on connecting rod on the either side of the particle will be treated as internal force. So we give a push along the frictionless horizontal surface and then examine the motion of a two bodies such a system. Then the complex motion of the system can be separated into two simple motions. One motion is the center of mass is moving with a constant velocity, and the system rotates with a constant rotational speed about the center of mass. Then let us describe it further. Let m1 represent the mass of the particle A, and let m2 represent the mass of the particle B. The vector r1 is from the coordinates, the xy coordinates is shown in the figure. It is to locate the mass m1, and m2 mass is its location is represented by r2 vector. This is relative to the origin O at any instant of time. Now we choose the coordinate system in this way that x is positive x is shown here, and the positive y is also shown here. The center of mass is then located at any time by this vector RCM, and RCM is equal to RCM is this vector is equal to the m1 r1 plus m2 r2 divided by the total mass m1 plus m2. Now, this again is the similar fractional mass, which is weighted with R1, and fractional mass of M2 is weighted with R2. M2 divided by the total mass is the fractional mass. The coordinate system locating the center of mass of our system at a particular time, it shows that it is in between this, and it is inclined more towards the heavy mass because that carries more friction. Now, if it moves further, you can see that the lighter particle has moved up and the heavier particle has moved down, and the new coordinate r prime is shown here. So it is not only the rotation but also the translation motion. But if we look at the center of mass, it is really following a translational motion in the straight line. The center of mass location is given by this vector RCM. Then x and y component are uh, given by the similar weightages with x coordinates. The x1 and x2 are the coordinates of the mass m1 and m2, and y1 and y2 are the coordinates for the m1 and m2 along the y direction. Therefore, center of mass x position, center of mass y position can be estimated using these two equations. Now, if we take the derivative of above equation with respect to time, then the velocity of the center of mass is given as dr over dt, and dr of the center of mass is given by this. Now, the r is containing r1 and r2, then the derivative will be taken of r1 and r2, then we get v1 and v2 vectors. So velocity of the center of mass is given as m1 v1 plus m2 v2 divided by m1 plus m2. So this is the velocity vector for the center of mass. If there is acceleration of the center of mass, then it can be calculated by taking another derivative of this velocity, and dv over dt will be the acceleration of the center of mass from this equation. And it will have m1 times acceleration a1 plus m2 times a2 divided by m1 plus m2, where a1 and a2 are the accelerations of particle m1 and m2 respectively, and they are basically the derivative of v1 and v2. So center of mass of a fixed object in any solid object whose location is determined by the way as shown above, we can locate we can find out the velocities, and we can find out the accelerations if we know the time dependence of these r coordinates. Let us elaborate further the two-particle system in more detailed manner and draw a free body diagram for M1, and then for the connecting rod, and then for the M2. Here, first diagram is for the mass M1, and we can see that there are the net force, which is F1R. This is the force on M1 due to the connecting rod. So F1R is the force on M1 due to the connecting rod, and its direction is shown in the positive x direction. The normal contact force is N1, and the downward gravitational force is M1G. So we know very well that the Newton's second law gives F1R equal to M1 times A1. And similarly for M2 mass, which is in the C diagram, you can see that the normal reaction is N2, and the force due to the gravity is M2 times G, and the reaction, this is the net force on M1 due to I'm sorry, this is the force on M2. M2 due to the connecting rod, it is F2R, and its direction is towards the rod and away from the mass M2, and it is in the negative x direction. Similarly, if we look at the rod, then this is the point for the rod, and there are two forces, FR2 and FR1. These are the net forces due to the rod on mass M2, and this is the force due to the rod on mass M1. And they are equal and opposite to the forces that are shown. So we can write F1R is equal to minus F R1. Similarly, F2R equal to minus times FR2. Combining these results, we get the sum of these two forces equal to 0. So the M1 acceleration in m1 plus m2 times acceleration in m2 is equal to the sum of the forces on the rod, which is equal to 0. So acceleration on the center of mass is equal to 0. Therefore, center of mass is moving with the constant velocity. The internal forces are just canceling each other. Remember, all the internal forces in this manner for many particle system do cancel each other. Now we look uh, again on this two particle system. When the external force is applied, then the net force on each particle is the vector sum of the external force and plus the internal forces. So the total is we get only the external force, which is m1 plus m2 times center of mass. It is as if the force is acting on the center of mass. For two particle system, we decompose the complex motion into the motion of center of mass and plus the other type of motion about the center of mass. If there is no net external force acting on the system, then center of mass will move with a constant velocity. If there is a net external force, then the motion of the center of mass will be found by assuming that net force is acting on the particle located at the center of mass, whose mass is equal to the sum of the two masses, or the total mass. So describing the two particle system, we can extend this further for many particle systems. And we see that if we consider a system of particles with the n particles in mind, with the mass m1, m2, m3, m4, up till mn, then the total mass will be m1 plus m2 plus m3, so on up till mn. Each particle in the system will be represented by its mass, m1, m2, m3, and its location will be given by the coordinates r1, r2, r3, and its components will remain as x1, y1, x2, y2, x3, y3, x4, y4, and so on. So it will have velocity vectors also, and it will have acceleration vectors also. So the net force on the particle will be the sum of the vector sum of the forces on a particular particle, which generally will differ from one particle to the other. And this force can be external force. Therefore, we can write the center of mass location as we have done for the two particles. For many particle system, it will be m1 r1 plus m2 r2 plus m3 r3 plus m4 r4, so on up till mn rn divided by the total mass. So that its x coordinate will be xm, x center of mass m1 x1 plus m2 x2 plus m3 x3, and so on until mn xn will be the last. Similar formula for y center of mass will be written m1 y1 plus m2 y2 plus m3 y3, and so on till mn yn divided by the total mass. So it is the fractional mass which is weighted with x coordinates of each individual particle. And we find out the center of mass from these weighting. Therefore, we can say that the many particle system will have a center of mass which will have velocity given as dr over dt of the center of mass, and the velocity of the center of mass can be written as 1 over m times m1 dr1 over dt plus m2 dr2 divided by dt plus m and so on up till mn dr n divided by dt. Or in the form of velocities, we can write m1 v1 plus m2 v2 plus m3 v3, so on divided by the total mass. In abbreviated form, we can write as a sum mn vn, and 1 divided by the mass. So if we differentiate the above, we can find out the acceleration. Acceleration of the center of mass is dv center of mass divided by dt, and it is similarly given as the derivative of the velocity of the particle 1 m1 times the derivative of the velocity of the particle 1, m2 times the derivative of the velocity of the particle number 2, and so on, which is really m1 acceleration multiplied by the acceleration of particle 1 a1 plus m2 a2 plus m3 a3 and so on until mn an. And in abbreviated form, it is mn an, the total sum from n is equal to 1 to n, divided by m. So m mass times acceleration is given by this, which is really the sum of the forces, all the forces, which is the net force. So net force can be external force because internal forces will cancel each other. The result is applied and can be used, and we have seen here that the Newton's law, second law, is applied for the individual particles. Then this is really the center of mass acceleration is given by these net forces on particle 1, net forces on particle 2, net forces on particle 3, and so on. The total force acting on the system of particle is thus equal to the total mass multiplied by the acceleration of the center of mass. And this is the equation which is just the Newton's second law for the system of n particles. They are treated as single particle of a mass m located at the center of mass, which will be moving with the velocity and experiencing acceleration due to the sum of all external forces. So overall translational motion of the system of particle can be analyzed using Newton's laws as if the mass of the whole system is concentrated at the center of mass and the external forces are applied at that point. Therefore, the mass, total mass multiplied by the acceleration of the center of mass as a vector quantity is given by equal to the sum of the external forces. If the net external forces on the system of particles is zero, then the center of mass will move with the constant velocity and the mass time acceleration of center of mass will be zero, or the net external forces will be zero. So these are the general results that are applied well to collect the individual particles information and also to uh, trace how the system will behave. Here we must remember that they are joined together by the internal forces in the solid form and they form a rigid body. For many particle system having a rigid body, this kind of application is of a tremendous utilization. The object itself may be executing any sort of a complicated motion, but the center of mass will be moving according to the above equation. And that's how the physics will continue the conversion of the n particle system into a center of mass system. Here we show the moon and the earth and their motion. You can see that this red colored path is that of the overall system's path. The center of mass of the Earth and Moon system is following nearly a circular path about the Sun. However, the Earth and the Moon both are rotating about their common center of mass, just like a baton. You can see that this is Earth, the bigger mass, and the smaller mass is the Moon, and the center of mass is shown by the black dot. And this is the joining path, and you can see it is the Moon is rotating here from this position to the next position, and then to the next position, and then to the next position, and then going downward and downward. And you see that this is sort of a rotation about the Earth. So we can also see a slight wobble in the orbit of the Earth, which is greatly exaggerated in this curve. The center of the mass of the Earth and Moon system, it actually lies within the Earth, but uh, because the Earth is always overlapping the orbital path of these, and here we have shown a little bit separated, but just to elaborate the point that the Moon and the Earth system must be treated as one object having a center of mass, and as if the total mass is concentrated at the center of mass, and it is moving in a perfect circular path. Let us do this one simple example. There are three particles of mass m1 equal to 1.2 kg, and m2 equal to 2.5 kg, and m3 equal to 3.4 kg. They are forming an equilateral triangle of edge length A equal to 140 centimeter. Question is, where is the center of mass of this system? So graphical representation is shown here. On x-axis, we have division 50, 100, and 150. On y-axis, we have again a division 50, 100, and 150. The smaller squares are showing the increments of 10. So we can find out the position. We have placed the coordinate system in such a manner that the origin of x and y coordinate system is at one mass m1. The other mass is m2, then third mass is m3. Now, the other mass is also placed on x-axis so that it has no component, y component in this configuration. However, M3 is having both X and Y component. So we find the components first. For M1, the mass is 1.2, and we see that the coordinates are 0, 0. So we write here 0 and 0 coordinates. Similarly, for M2, the mass is 2.5 kg, and it is at X equal to 140. Position is 140 because of the length of this triangle, and 140 is x coordinate, but it has no y coordinate, so it is equal to 0. The third position is located at, from this we can find out, it is located at 70 along the x-axis. So this is 50, then 60, and then 70 is the position on x-axis. Similarly, on the y-axis, it is 120 position, 120 position, 120 position. This is 100, 110, and 120 is the position. Then using this, we find out the coordinate of center of mass. Coordinates are the x coordinate and the y coordinate, and for that we use 1 divided by m, sum of the masses multiplied by the x position. So m1 x1 plus m2 x2 plus m3 x3 divided by m, and we plug in the values and find out the simplified answer as 83. Similarly, for y coordinates, the m1 y1 plus m2 y2 plus m3 y3 divided by the total mass, and we plug in the values and get the 58. And that's how the answer comes. Now we can locate this center of mass. It is this red dot, the 83 position on x-axis. This is 50, 60, 70, 80, and slightly higher 83. And on y-axis, it is 58. This is 50, this is 60, and it is slightly less than 60. It is this position. So figuring out center of mass for this problem was not really a big deal. Only we had to learn how to find out the coordinates from this graph. Most important was this, and the rest of the weighting was done. And a clever way of putting the coordinates axis on one mass reduced the problem. We could have made this also some coordinate, but the answer would have been again the same position inside this triangle. So with this, we stop here this lecture, and we will continue our discussion on the systems of particles in part 2, and we will try to find out the center of mass for different shapes and sizes in coming lectures. Thank you so much.